In this tutorial, we're going to learn how to use the robot memory and the embodied agentic task planner in EMOS. We're going to build a recipe for a robot that can explore a room, remember what it saw, and then go anywhere you ask just based on its memory. To do this, we're going to be using, of course, the navigation stack from EMOS and two other main components. The first one is Cortex. Cortex is the LLM-powered task planner in EMOS. You give it commands and ask it in plain language. It figures out the plan, how to execute it, calls the right tools and capabilities from the robotic system, and it also adapts the plan during execution and monitors the execution steps. The second component we're going to be using is eMEM. eMEM is EMOS spatial-temporal memory for the robot. As the robot moves around in the space, it builds up a map in its memory. Every place, object, incident, event that it encountered is pinned to a specific coordinate, a timestamp, and it's ready to be queried from a specific layer in the robot's memory. We're going to be building our recipe today, and then we're going to test it first in simulation with the TurtleBot 3 robot, and then we're going to test the exact same recipe on a real quadruped robot, which is Light 3 from Deep Robotics. Okay, so let's see how we're going to build this recipe. So this is the landing page of EMOS documentation. If you go to the planning and manipulation part, you would find multiple tutorials and helpful walkthroughs about Cortex, the agentic harness, about using memory with Cortex. And if you go here to Cortex driving the full stack, you would actually find a very similar recipe to the system that we want to build today. So you can see here you can build a system that has the perception, the spatial memory, the voice of the robot, navigation, and then the embodied agent using Cortex. You would find here a step-by-step walkthrough to building a similar recipe to what we want to do today. So another way to do this, if you go to the landing page of EMOS, and if you go down, you would find an AI-assisted coding section. So if you click on this part here, you would get a prompt that you can give to your LLM assistant to help you code whatever recipe you want. Okay, so let's go straight into the recipe that we have built for this tutorial. So to build the recipe, first we need to import a few primitives to define the robot that we would be using this recipe. So a few classes related to the robot type, geometry, and control limits. This is for the navigation part of EMOS. Then we need to import a few components from EMOS navigation stack Kompass. So we got the controller, the drive manager, local mapper, planner, and the map server. Then we imported the intelligence components from agents.components. We got the vision, cortex, and memory, and a few configuration classes for them. I also imported an OLAMA model and an OLAMA client that I would be using for my component. Finally, we just need a few primitives from ROS to build our system. So topics are the connecting pipes between the different components. Launcher is the thing that will bring up my system. And I also got a memory layer that I would be using for my memory component. So we start by configuring the robot. So here I have the configuration for the TurtleBot robot that I would be using in simulation in the first part of this tutorial. Then we start by defining the planner model client. So I'm using a Qwen 3.5 latest model. I will be using this for Cortex. And I don't have any host specified here. It means that the model would be running on localhost. Then I have a few topics that I need for my components. So the image topic for the camera that is on board of the robot. I have a detections topic. And the location, the position topic of the robot. Then the first component we are defining here is our vision component. So the vision component would take the camera images of the robot as an input, and as an output, it would provide the detections. The trigger is the coming images. So every time a new image arrives, it would trigger the inference of the detection model. In my configuration, I set enable local classifiers to true, and I didn't provide a model client. It means that the vision component would automatically deploy a local model on edge. Then we start by defining the memory component. So first I defined the embedding a client, which is another Olama client that I would be using for this component. And then here you can define the layers. So as you see, I only defined one memory layer, which subscribes to the detections topic, and it has temporal change enabled. I can add as many layers as I want here. So for example, I can add another memory layer that subscribes to the robot battery, another memory layer that subscribes to some LLM output for which I am asking a fixed question like what type of a room is this? Are there any incidents in this room, and so on and so forth, depending on the application. For now, we're going to keep it simple and just subscribe to the detections topic. We can explore using a more elaborate memory in other tutorials. I also provided the position topic. So each observation in the memory is pinned to a specific coordinates for the robot. I gave it the embedding clients, and then in the memory config, what is important to provide is the database path where you want to be saving this memory. And the trigger is 10 seconds. So every 10 seconds, it would save a new observation to the memory. Then we started to configure Cortex. So Cortex, you need to provide it with a model client, which is the planner client that we defined earlier. The output is just a text output, so it can be a string or a streaming string. Here I provided with a streaming string, so the output can be more live on the user UI. And then this next part is about configuring the navigation stack. So all the navigation components, we already saw this in a previous tutorial, so I'm just gonna go quickly here. So as you see, we configured the planner to be running as an action server. So this would be our entry point into the navigation stack. I defined the algorithm that my controller would be using. I defined the robot command output from the drive manager. I have my local mapper here taking as an input the sensor data of the robot, and then serving the map file. And since I'll be using the simulation, I can take the static map directly from Kompass sim package, which I would be using to run the simulation. Then finally, to set up my system, I got my launcher. I add my components package per package. So first I added all the components from the navigation engine of EMOS, then all the intelligence components from EMOS, and I enabled multiprocessing for both. So each component would run in its own process. Then I need to set all my robot configuration to the launcher. So I gave it my robot and my robot frames. So as I said, this is the only part that is going to change between simulation and deployment. I give it the location topic for the robot, and then to have a user interface so I can communicate with my robot during runtime and send commands, I enabled the user interface. So you just do launcher.enable UI, and you provided all the stuff that you want as an output to the UI and everything that you want as an input. So as an input, I'm just adding one entry point, which is Cortex main action input. So this would be my entry point to send commands to the robot. And then as an output, I wanted to see the global map and the global plan and the location of the robot, so I can see the robot executing commands and navigating. I also added the output from Cortex, so I can see the replies from the robot. I can also add here, for example, the camera image topic. So we call it image 0. So I can also see the camera images for the robot. And then finally, you just do launcher.bringup and you can run the recipe. So let's start by running our recipe in simulation. I'll be using a simulation from Kompass Sim package, which is a package that we prepared with a few pre-configured simulation environments to get you started quickly. You will find the link in the description. I'll be using the one with the TurtleBot 3 robot configured with an RGB camera and WeBot simulator. After running the simulation, I ran the recipe that we just saw together. And this is the UI that we got with all the outputs that we configured, the map, the robot on the map, the robot's frontal camera, and as you can see, the task input for Cortex. So I'll just ask Cortex to set up the system for exploration. What it did behind the scene is that it opened a new episode in memory. That is the session where everything the robot sees from here on is going to get stored. Then I started to move the robot around in the room. As it moves, it's supposed to be looking to the world through its camera, quietly adding all these observations to the memory. Now, this memory is persistent. Different runs, different days, it's the same robots, still the same memory. I'm going to actually kill my recipe and start it fresh. So I removed the robot camera from the UI output. So as you can see here, I don't see it anymore. And I'm going to investigate its memory. So I started by asking it how many plants did it see during its exploration of the room. So as you can see here, Cortex queried the memory. It got multiple observations for the plants in the room, and it actually did more high-level reasoning for clustering these points, and it estimated having 2 to 3 plants, which is actually pretty good because there are 3 potted plants in the room. Alright, so now the last step. Let's tie it all together. I'm going to ask it to go to the potted plant near the fridge, which is actually the one on the left side of the map. So Cortex actually was able to retrieve the location from the memory, and then the next step in its plan was to trigger the navigation system that we added in the recipe. So as you can see, the point got sent to the planner. You have the global path that leads to the potted plant, and the robot started moving there until it reached the plant that is actually next to the fridge. Now let's deploy the exact same recipe on an actual robot that I have here with me in the office, which is the Light 3 quadruped from Deep Robotics. We will be running the recipe on the robot's Jetson Orin board, and we will be using the 2D laser scan and the Intel RealSense camera of the robot for the images. So I will be using the exact same recipe that I used in my simulation, and the recipe is directly portable into real robot. The only thing that I need to change is the configuration of the robot that would be using the recipe and using the navigation stack. So here, for example, for the geometry, instead of a cylinder, which was the TurtleBot 3 robot, I'm going to be using a box for the shape of this quadruped. I would update the geometry parameters to the size of the Light 3, and I would also update the acceleration limits to whatever limits that I want when testing in the office. So this is the only part that needs updating, and then I would update the name of the image 0 topic to match the name of the Intel RealSense topic. Other than that, the recipe stays exactly the same. So I'm going to put this on board of the robot, and then we can run it together. So I moved the recipe to the robot, I turned on all the necessary hardware, and I ran the recipe using EMOS. And this is the user interface that I got. You can see here, this is the map for my office where I'm testing right now, and this is the robot. Actually, if you click on visualize, you can see all the system that we have running right now. So you can see the memory component that we added, the detection component that is feeding the memory. You can see Cortex, and as you can see, it doesn't have many topic links to the other components, but it has a server client architecture with all of them, so it can call any tool from any component. And then you can see here all the rest of our navigation stack from the map server, the planner, local mapper, all the way down to the drive manager that is sending the command. And if you click on any component, you can also see more details about the configuration. So the robot already did the similar exploration in the office, so it has multiple locations pinned to its memory, and I'm going now to ask it to go to the door. So querying items from the memory happens in the planning phase. So now Cortex should be querying the door location and then sending the goal to the navigation stack. So as you can see, it got the location of the door. And then as you can see on the map, we got the global plan, and voila, the robot starts moving to the door. So in this tutorial, we learned how to create an embodied agent that can remember, explore, recall memories, and also execute commands and high-level plans. You can pull and try the exact same recipe in your simulation or on your robot. Also, don't hesitate to use the llms.txt in EMOS to have your digital agent help you write recipes.